we're going to jump right into OLS. We're going to start with a couple pictures. So I got two graphs of some different variables, and I'm not focused on details of what's on the axis, but just concentrate on what those graphs are presenting. On the left side, we can see the data pretty well shaped. Seems like a pretty tight correlation. If we drew a line there, it'd be a positive slope over on the left-hand side. In contrast, the graph on the right just looks kind of random. These are very different data. So we want to find a way to say how well a simple line can represent a whole collection of data points. A line can be a way to summarize all those dots in a much more efficient way. Want to find a line that's in a certain sense close to each value of y. Close to is typically defined as minimizing the average squared distance. That's the vertical distance. That's why it's called least squares, OLS, or at least that's the LS part of least squares. And that's the ordinary, the one that we come back to again and again and again. That's the O there in OLS. So there's a formula for these distances and what minimizes. We'll circle back around later. First ask, well, why is it useful? It is a very powerful abstraction simplification. If I say y is some value beta naught plus beta 1 times x plus epsilon, then if that epsilon is small, I'm taking that whole collection of data, all those dots, all that stuff going on in those pictures, reducing it down to just beta naught and beta 1, just two values. It's a lot of compression of how much data I need to keep track of. Beta 1, the slope, can be greater or less than 0. If beta 1 is less than 0, then the slope is negative, and there's a negative relationship between x and y. If beta 1 is greater than 0, then the slope is positive, and there's a positive relationship between x and y. If beta 1 is 0, then there's no relationship between x and y. Now, a negative relationship is not the same as 0. Example I sometimes used, remember when we were rebellious teenagers doing exactly the opposite of whatever our parents told us to do. We might not have quite realized it, but we were not showing independence. If, when somebody tells you to do one thing, you always do exactly the opposite, then you're still being completely determined by that other person. Only if there's 0 relationship are you independent. Sometimes you do, sometimes you don't. That's a 0 relationship. Independence. Estimating beta 1 equal to 0 would be a case where there's no relationship, such as the line in that other graph there that I've shown. Now in finance, sometimes other situations, you might hear different notation. Instead of being written as beta naught plus beta 1 times x, you see it written as alpha plus beta times x. If you've heard expressions in finance like chasing alpha or looking for a low beta, that's from that representation of the linear regression model. X would be the market return, Y the return on a particular portfolio. If it's an index fund, then alpha is going to be nearly 0 and beta nearly 1. That's how they replicate the market. On the other hand, if you have a completely risk-free portfolio, then beta is 0. Market goes up, market goes down, you get the same alpha return. Well, this isn't a finance class, so we'll go back to the more general case. Hint, looking ahead, we add more x values, the beta naught plus beta 1, that works better for extensions. We don't want to learn the whole Greek alphabet. And we could, but, probably not. So here we go back to these two pictures. Now I've drawn the regression line through them. You can see there's a positive relationship in one case, the other case, pretty much 0. So how do we tell the difference? Now, there are a lot of possible criteria. One could just be an aesthetic judgment, which, I don't want to throw out as a complete straw man because it's not entirely irrelevant. There are cases where, that shades into the next consideration. Is it persuasive? If it looks lovely, then perhaps it can be good at persuading somebody. Now you can ask, is it useful? That's sometimes a slightly different rationale than being persuasive. Can you ask, is it precise? Now that's equivalent to asking how big is the epsilon term relative to the other terms. That's a bit easier to measure and formalize. It's useful to keep in mind they're each going to be distinct questions. We have a lot of measures to say how precise is this, but that doesn't necessarily provide any judgment about is it persuasive, is it useful. One of the questions we might ask is how can we guard against being fooled, against thinking that there's a relationship. Maybe it looks like the dots are kind of wiggling around in some way, but they're not actually. Maybe I'm just being fooled. People draw constellations in the night sky. Sometimes it looks like the stars just line up in a row, and we humans draw a line there. Ancient people thought that some gods put that line of stars there to communicate something to us mortals. But the apparent locations of the stars are entirely random. So how do we guard against being fooled, against seeing lines that aren't really there? That's what I've been calling as thinking like a statistician. We ask, what if the slope were truly zero? What kind of things would I see in that case? Versus what would be a surprise if there were no relationship? What would surprise me? Oh, I thought it was zero, but it's actually kind of weird to all line up like that. So let's go through a little experiment. Here we have y equals 10 plus 2x plus e, the error. And in this case, that error is going to be really large. That's the plot there. You could put a line through those dots. Reasonable people could argue about what kind of line, but the line that minimizes the squared vertical distance has a slope of 1.61813. Okay, how do I guard against being fooled? What if actually there was zero correlation? What if the true value of beta 1 were 0? I could still randomly get some y values that would look like a slope. I estimate the slope on those actually genuinely uncorrelated values. I do that 10,000 times just to see what kind of results I get. This histogram shows the estimated values of beta 1 from 10,000 simulations. We see the most common result is near 0, but a fraction of the 10,000 gave values as low as -3 or as high as +3. You can see my original estimate of 1.61813 is a bit of a distance away from 0. Only 659 out of the 10,000 simulations gave a slope estimate that was that big or even bigger. That would be a p-value of 6.59, which is not greater than 5%, so we would not reject the null at a 5% level of significance. Now, hopefully some part of your brain is now firing some neurons. Oh, hey, that really looks kind of like the dice example that we did in class. Because, yes, this is exactly the same framework. Under a pretty general set of conditions, the OLS slope coefficient has a normal distribution. Thus, the estimate of beta divided by the standard error of beta is going to have a standard normal distribution. And we often call it the t-stat or t-statistic because if n is small, then that's a t distribution. But in most cases we're going to be working with here, we'll have a lot of observations. So it's going to have a standard normal distribution, but we still call it a t-stat just for tradition. So to test against the null hypothesis of 0, which is the most common, we'd form the test statistic beta hat minus 0 divided by the standard error of beta. If we want to test against some other value, not 0, then we put that in. But it's very common, normal. Sorry, bad joke. Normal. It's really common to test against 0 because that's the no relationship. If there's nothing going on between x and y, no correlation, no relationship at all, then I'd expect to see some value near 0. So most computer programs automatically calculate a p-value against the null hypothesis of 0. Explained this earlier. We talked about the estimate, we talked about the p-value, we talked about the confidence interval, any of those. They have the same ultimate relationship and making the same statistical tests. They're just different ways of saying the exact same thing. It's super easy to calculate t-stats and p-values, so most computer programs are just going to spit them out automatically. Now, for a univariate regression, just one x variable, statistical significance for the slope coefficient is the same as statistical significance for the overall regression. Later, we're going to add in more x variables, and then that result drops off. But to get these more easy interpretations, there's inevitably some cost. The cost of this nice, easy result is we have to make some assumptions. The biggest, hugest, most crucial assumption is the first one, that X completely specifies the causes of Y. There's nothing omitted, nothing else going on. Y is determined by X and some completely random error, and there's nothing else there. That is a strong assumption. It's a big deal. One of the reasons we'll often add more X variables is because of that. Now we also have to worry, might be there's some reverse causation. Is there a reason to think that Y is going to cause X? We can also assume that X causes Y in a linear manner, and that's why we're drawing a line. A line is linear. We also assume the errors are normally distributed, which is crucial for cases where we have small degrees of freedom. If we have more observations, we can get away with slightly looser restrictions. Maybe assume the error and the X variables have fourth moments defined. It's pretty typically true. Sometimes in finance you might worry. Next, at least at the beginning, we assume the errors all have the same standard deviation, which is what we call homoscedasticity. Or the errors are not heteroscedastic. There's no heteroscedasticity. Yeah, those are big words. They're often used for impressing outsiders. Finally, we assume the errors are going to be all independent of each other. You might imagine cases, particularly in a time series, where a miss in one direction means you'd expect to see a miss in the opposite direction next. Some sort of overcorrection or something. But with all these assumptions, we can say that OLS estimators are unbiased and consistent. In fact, they are blue, the best linear unbiased estimate. Which sounds impressive, except it's best among the rather small category of linear unbiased estimators. It's kind of like saying somebody's the best looking economist. It's not really making such a big statement as you might hope. Anyway, we do have some formulas. We don't really need to know them since, of course, the computer just takes care of all that. But we'll talk a bit about how they're derived. Simple problem set up as xi, where that is a whole list of y values from 1 to n. And that's equal to beta naught plus beta 1 times x plus some epsilon. So the x and y are known, and we're going to choose beta naught and beta 1 to minimize the error. So from calculus, you know exactly how do I minimize something? Take the derivative, set it equal to 0. That's easy. And that's one of the big reasons we have squared errors here, because taking the derivative of a square term, we can do that with some calculus. That's easy. If we wanted instead to minimize the absolute value of the errors, say, then you could, except taking the derivative of the absolute value can be a pain in the ass. Especially right around 0, which is where I want the errors to be. It can be computed, but historically that would take more computational power. Least squares has been around for literally centuries because people could do it without computers. So with some calculus, I want to minimize the squared error values, choosing some values of beta. There are a bunch of steps. It's not conceptually that difficult. You find beta 1 is going to be the sum of x minus x bar times y minus y bar divided by the sum of x minus x bar quantity squared. Key thing to note in the formula is the top of it looks very similar to the formula for covariance. The whole formula looks like the formula for correlation, except not quite right. The correlation would have an additional y minus y bar squared on the bottom. The formula is the covariance divided by the variance of just x. So one reason we might have trouble getting a good estimate of beta 1 is if the variance of x is just really small. We'd be dividing by a number close to 0, which, that's kind of bad. So then to some extent, the intercept term is almost a nuisance parameter. It's just calculated to make the rest of the regression work. It doesn't have to have too much meaning in and of itself. Makes the average error equal to 0. The beta 1 hat term is the slope, dy dx, delta y, delta x, all that stuff you learned back in algebra class when you were an infant, right? You can get predicted values of y by putting in the estimated value of the coefficient, multiplying that by each x. It's all enormously useful, and it's called ordinary least squares, OLS, because it's just so ordinarily done, so useful as a first step. It's not commonly the last step though, but we'll get to those, some of those.